Hello guys, today we're going to study 4.5 exponential growth and decay. So here we have the mathematical model for exponential growth and decay is given by two forms right here. F of t equal to a sub 0 e to the kt power, or we can write it as a equal to a sub 0 e to the kt power. So here we have the graph. When we have a k is greater than 0, that means we're going to have an increasing. If our k is less than 0, then we're going to have a graph is decreasing. That means it's decay. Okay, one's growth, one's decay. Alright, let's take a look at example 1. Example 1, modeling the growth of the U.S. population. The graph shows the U.S. population in millions for 5 selected years from 1970 through 2010. In 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. Part A, the question is find the exponential growth function that models the data for 1970 through 2010. So we're going to use the exponential growth model. We know the exponential growth function look like this: a equal to a sub 0 multiply e to the kt power. So in this case, we started 1970. So I'm going to write a equal to, in 1970 we have the population 203.3. What a sub 0 means, that means where you begin. Okay, this is the amount we begin with right here. I'm going to highlight it. And then we're going to write the e to the kt power. Okay, so once we have this, we also have to look at other piece of information given to us. It says by 2010, it had grown to 308.7 million. That means by 2010, you're going to have an end amount, which you're going to replace with your a, 308.7. Okay, all I did is just a substitution because this is my end amount, equal to 203.3 e to the kt power. So what is t? If you think about it, we started in 1970, we end at 2010. So t is a year, so that means I can use the 2010 minus 1970, which gave us 40. That means how many years has passed, right? So t replaced with 40. So once we have this, because we have a one variable, one equation, now we can solve it. We can divide both sides, okay, by 203.3, because then I can cancel this part out, right? So I'm going to divide this both sides. So I'm going to have what left? So the right hand side we have left is e to the 40k power. Okay. On the left hand side we have 308.7 over 203.3. Instead of writing this on the left side, I wrote it on the right hand side because I like the variable on the left side, my number on the right hand side. So now we see the base is the e. The e is not 10. I can actually take a natural log both sides. Right? We have learned this. When we take a natural log both sides, we have a natural log, we have an e, they're going to be canceled out. Then I have a 40k equal to natural log 308.7 over 203.3. 40k equal to this whole thing. How to solve for k is just going to divide by 40 both sides. And then they're going to be canceled out. So my final answer, that will be k equal to natural log 308.7 over 203.3 over 40. We plug this whole thing inside your calculator, we're going to get around 0.01. That is our k. Because the question is asking you, find a exponential growth function. So all you have to do now is bring this back. So that means we're going to have a equal to 203.3 e to the 0.01 t. That is our exponential growth function. Let's look at part B. Part B, by which year will the U.S. population reach 335 million? Because we found the exponential function already, so that means we're going to replace our a with 335. 335 million, because that is the end amount, and then equal to 203.3 e to the 0.01 t power. Okay, All we're doing is, maybe I'll use a color right here, 335 I'm going to replace with A. So now we're just going to solve this equation. Alright guys, I done this pretty quick because it's very similar to part A. So we're just going to solve it, and then we take a natural log both sides, and then we're just divide 0.01 both sides, and then we're going to plug this whole thing inside your calculator. We get the time is 50 years. Okay? You got to remember the question asking you, by which year will the US population reach this 335 million? That means we have to use 1970, add our 50 years. And then that will give us 2020. We can say by the year of 2020, the US population will reach 335 million. That is our final answer. Okay guys, let's move on. Example 2. Example 2, we have a carbon-14 dating the Dead Sea Scrolls. So part A, use the fact that after 5,715 years of a given amount of carbon-14, we'll have decayed to half the original amount to find the exponential decay model for carbon-14. Okay, so here is our question. Again, similar illustration, but the only difference this time is the increasing, you're going to have a decay model. So in your head, you have to realize, okay, in the end, my K I get must be negative because it's decreasing, it's decay. We're going to start writing down A equal to A sub 0 e to the kt power. So you have to realize that A sub 0 is where we begin. A is what's the amount in the end. Let's write down the ones we actually know what is. Okay, so the certain years, that means I can replace this T with 5,715. We also know, okay, a given amount, that is actually our initial amount, right? It's a given amount. We'll have a decay to half the original amount. Okay, in the end, you have to realize that A is actually half of the original amount. Okay, that's why I can replace this with half the original amount. And then we have A sub 0, we have a E, so we don't know K, but we know T is 5715, half the original. Okay, that's where this half come from. So now you have A sub 0, both sides. If you divide it both sides, they're going to be gone, right? So they no longer is my variable anymore. So I'm going to have a e to the k, so let me just write it down. That'll be e to the 5715k. Again, this type of question, all we have to do is just take a natural log both sides. So then natural log e, they're going to be cancelled, very similar to what we've done so far. So I'm just going to write 5715k equal to natural log. I can rewrite this as 0.5. Divided by 5,715 both sides. Then this is going to be cancelled out. Then we're going to have a k equal to, so we can plug this inside your calculator. Then this is give you around, remember you should get a negative number, negative 0.000121. So that is your k. Because the questions are asking you, we want you to find the exponential decay model. So which means we have to bring this back to your original equation. Then your function should look like A equal to A sub 0 e to the negative 0.000121 t. Okay, so that is my part A. So now we're going to use that model to solve part B. So part B, you can pause this video to read it, but the main idea is to look at here. The scroll actually contains 70-60% is the original carbon-14. And then estimate the age of the Dead Sea Scrolls. From part A, we have the exponential decay model. So I just recopy this. So what happens is this time we have 76% of original carbon-14. Okay, we know the original is A sub 0, and then 76% is just actually going to be 0.76 times A sub 0. Then we're just going to set this up and then solve for t. The main thing is you have to make sure you know how to set it up. Once you find the part A, part B is actually quite simple. You're just going to solve it. This time, instead of dividing, I know they're going to be canceled out. So I'm just going to write it down, cancel out. So we're going to have 0.76 equal to e to the negative 0.000121t. And then we're going to take a natural log both sides. Okay, they're going to be gone. Again, the process is exactly the same. So I just done this really quick. Once we take a natural log, and then the rest of the stuff is just a simple math. So you take a natural log, and then you have a log and an e. Natural log and e, they're going to cancel out. And then you're going to have this whole thing. You divide this negative 0.00121 both sides, and then you plug this inside your calculator. You get your t is 2,268 years. That is your final answer. Alright, let's move on to the next type of question. So here we have logistic growth model. This some mathematician already derived this for you. All you have to know is how to use it. Okay, so we have a mathematical model for the limited logistic growth. It's given by f of t equal to c over 1 plus a times e to negative bt, or a equal to c over 1 plus a multiply e to the negative bt power. One will use f of t, one will use a. One thing I want you to write it down. Our c, in both cases, our c is just the limiting size. Okay, so I'm going to explain to you more in example 3. Example 3, we have the function f of t equal to 30,000 over 1 plus 20 e to the negative 1.5t. Describes the number of people f of t who have become ill with influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. So part A asking you how many people become ill at the beginning. When we talk about begin, means your t is 0. Okay, all you have to do is you're just going to find the f of a t will replace with 0, and then everything else you just copy it down. It's just a substitution. So that will be e to negative 1.5. We said the t is 0. Okay, the begin means 0. We'll just substitute this, and then if you think about this, e to the 0th power just give you 1, right? This actually is 30,000 over 21. It's around 1429. And then the second question, how many people were ill by the end of the 4th week? So now we're talking about 4th week, it's just plug in 4 in your function. So you can do this by using calculator. So you should get around 28,583 people. And then part 3 is, what is the limiting size of f of t, the population that became ill? Go back and look what I told you. Our c, which is 30,000, in this case, c is our limiting size. Because we have total 30,000 people live there, of course, the limiting size, that will be 30,000. I'm going to write it down. That's 30,000 because it's the limiting size. Alright guys, that is your 4.5. Thank you very much for watching the video. I'll see you guys next time.